Okay, so let's begin. So I'll have to get those notes that we did on Friday. We'll have to finish those up probably tomorrow or maybe at the end of this period if we get through this. Let's talk some more about gravitational fields. For those of you that have been away for a day or two, we're basically looking at gravitational fields. All of the kinematics and dynamics that you've been learning about, we're now going to flip vertically. The acceleration is almost always going to be 9.8 because things generally happen on Earth, where the gravity is 9.8. Friction force will be air resistance. Other than that, it'll sort of be a lot of the same, but we will talk about gravitational fields. And then in the second half of the unit, which will be coming up near the end of this week, we'll be talking about frictional force, and we'll actually flip everything sideways, and we're going to look more into friction and how that works. So today I'm going to answer the age-old question. You probably wondered, what would happen if you dug a hole all the way through the Earth and jumped in? I'm going to answer that question today.
You'd probably be going so fast that you'd fall.
I will answer that question today. Okay, so read along with me, please, here. And you may want to, if you have a highlighter or a pencil, you may want to make some notes or highlights as we go. All right, so follow along with me, please. Follow along with me, please. Excellent. The Earth pulls on the moon.
Yes.
We regard this as action at a distance, and you'll notice that action at a distance is in italics because it's important.
Highlight.
Action at a distance. There is a force, right? The Earth pulls on the moon. Is there a big, long, giant elastic band between the Earth and the moon? No, there's nothing there. It is some mysterious force that exists without contact. Like if I want to push on the tape dispenser, I have to actually touch it. I have not completed my Jedi Master training. I am not able to push on the tape dispenser without touching it. It would be very cool if I could. One of these days I'm going to try to rig that up. Yeah. If I could just go like this and have like someone with a string hiding under there and just pull it. Wouldn't you guys freak out?
No.
I might.
That'd be pretty funny.
All right, so this is called action at a distance because the Earth and Moon interact with each other even though they are not in contact. That is what I mean by action at a distance. And why am I repeating myself over and over again like that? So action at a distance refers to an interaction without contact. Or we can look at this in a different way. We can regard the moon as interacting with the gravitational field of the Earth. Okay? So we can say that the moon doesn't contact the Earth, but the moon does contact the Earth's gravitational field, that mysterious, invisible force field. The properties of the space surrounding any mass can be considered to be altered in such a way that another mass introduced to this region will experience a force. This alteration of space is the gravitational field. It's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the masses of the Earth and other planets or stars that are the source of these fields. The field concept plays an in-between role in our thinking about the forces between different masses. So, humans tend to have this difficulty in imagining a force being able to be in contact or being able to push or pull something without touching it, right? But if you think about the force field idea, right? I have a gravitational field around me. The tape dispenser that I'm standing close to is interacting with it. Why is it not racing towards me?
Friction.
The friction. Why are you doing that, Hannah?
I'm not meaning to, I laughed and it happened.
Can you stop? The friction between the tape dispenser and the countertop is far more than the gravitational pull of myself. I'm not large enough yet. Hopefully not to be large enough. So, a gravitational field is an example of a force field. For something in the space experiences a force due to the field. Another force field you may be familiar with is a magnetic field. You've probably seen iron filings lined up in patterns around a magnet. The pattern of the filing shows the strength and the direction of the magnetic field at different points in the space around the magnet. And I'm going to talk about magnetic fields in the future, probably not till January. Where the fire lines are closest together, the field is strongest. The direction of the fire line shows the direction of the field at each point. Now, the pattern of the Earth's gravitational field can be represented by field lines like in 11.4 there, and you can see that on the left-hand side of your page there, right? And for those of you that are watching this at home, they can see it here on the left-hand side as well, right? So, like the iron filings around a magnet, the field lines are close together where the gravitational field is stronger. At each point on a field line, the direction of the field at that point is along the line. Arrows show the field direction. Which way are the arrows pointing? Not just left. Inside, toward the center of the Earth, right? Gravitational force field is obviously towards the center. A particle, astronaut, spaceship, or any mass in the vicinity of the Earth will be accelerated in the direction of the field line at that location. Now, the strength of the Earth's gravitational field, like the strength of its force on objects, follows the inverse square law. What do I mean by inverse square law? Anybody know? I mean,
The gravitational field at any point is driven by the force on a unit mass placed there. The force F is in joules, and the field strength is specified. M in its units are per centimeter.
I don't even know where he's reading that from. Oh, oh, it's the asterisk. Oh, okay, yeah. But what do I mean by inverse square law, though? Inverse square law means this, and there's a lovely spot at the bottom of the page for you to write this down.
Cube roots.
Inverse square law means that if it's 2 times as far,
If it's two,
you don't have to say if it's, you just have to say 2 times.
okay.
You have to get better at abbreviating. Twice as far is going to mean, because it's inverse squared,
Equals 1/2 is far.
1/2 squared, or 1/4 times as strong.
Whoa. Two far means one, what?
It's inverse squared, and so 2 times
Oh, I get it.
as far means 1/2 squared.
Square,
No. Squared as an exponent.
but there's no B.
Squared. Inverse square law. Yeah.
Or-
It doesn't mean like a square that's flipped inside out.
Or 1/4.
1/4 at times as strong. It means that if you were 3 times as far away, if one planet is 3 times farther away from the sun than another, then the gravity is 1/3 squared, or 1/9 times as strong. Or you could say 9 times weaker. Right? What if it's 1.5 times farther? Inverse square. 1/1.5 squared. Which is 15 squared, anybody?
No.
You don't know that's 2.25?
No.
Yeah, it's 2.25.
I didn't think.
All right. So those of you listening at home will need to get that written down from someone who was here.
Why can't you write it on your?
I can't. I don't have the pen thingy for my laptop. Yeah.
You type it.
I could. They can get it for you guys. So that's what the inverse square law refers to. Make sure you know that. Put a asterisk beside that.
What's an asterisk?
A star.
Star.
It is strongest near the Earth's surface and weakens with increasing distance from the Earth. Now, you'll also notice that picture there. You'll also notice that picture of the Earth with the gravitational field lines like this, right? This is coming up in the notes as well. But where the lines are close together, really, you two, you really have to listen. Like to me, no to me, not to each other, to me. Stop. You'll find your mark will go up if you stop visiting in class.
My mouth is too great.
It can be better. It can. Where the field lines are closest together near the Earth, the field is strongest, and where way out here, where they're farther apart, it is
Weaker.
weaker. It's actually based on what we call the density of field lines. How many lines there are per square inch kind of thing, or square centimeter. All right, flip the page. The gravitational field of the Earth exists inside the Earth as well. If you've ever dug a hole and stood in it, you will know that gravity exists there. Yeah, I mean, wow, right? I mean, dig a hole in the sandbox, still gravity there, right? So digging a hole doesn't get rid of gravity. To investigate the field beneath the surface, imagine a hole drilled completely through the Earth, say from the North Pole to the South Pole. And you'll see on the paper there, basically they've shown the Earth completely sliced in two. And we're not talking about slicing it into like an orange or an apple or something or other. We're talking about drilling a hole through the middle, right? Okay, so that's more like a dotted kind of line, right?
Can you get stuck in the middle?
I'm going to answer that.
Did you drill a hole into that?
I did not.
You just went there?
I'm going to explain.
It has some.
Forget about impracticality such as things as lava and high temperatures, and maybe that you might get hungry, need a snack along the way.
Yeah.
Consider the kind of motion that you would undergo if you fell into such a hole. If you started at the North Pole end, you would fall and gain speed all the way down to the center. You would accelerate. At what speed? Sorry, at what rate? At 9.8 meters per second squared. But after some point in time, you would actually be closer to the center of the Earth. So would your gravity be more?
Yeah.
One might think yes, because the field lines would be closer together. You're closer to the center. Inverse square law, the closer you get to the center, the more gravity. But there's a problem. Gravity is also dependent upon the mass of the thing that you are being attracted to. As you get closer to the center, more and more of the mass is no longer below you, if I could use that term, but some of the mass is now actually above you, and you are in fact attracted to it. So you are attracted to the mass below you and the mass that is now above you.
You know, rip you apart.
So how does this all work out? Well, let's read. So you would fall in at the North Pole, you'd fall and gain speed all the way down to the center, and then overshoot. What do they mean by that? It means you'd go flying right past, because as you're about a quarter of the way down, sorry, about halfway down, you see where it says A equals G divided by 2? The gravity would actually be about 4.9. And that's not because you're getting closer to the center, it's getting weaker because there's less mass to be attracted to. That's not entirely accurate scale-wise, but it's close enough. What would be the acceleration at exactly the, right exactly the center? It'd be 0. Now that's assuming that the Earth is actually a complete sphere, a perfect circle, perfect round object. It is not. It's an ellipsoid. It's actually flatter at the top and the bottom, and by a significant amount. Like I think it's like 23 miles difference, something like that, right? It's actually wider at the equator than it is from top to bottom. Okay, it's because of the spinning thing, and there's all sorts of reasons. Okay, so you would in fact now, if the gravitational field strength is 0 at the center, would you stop and just float there? No, because you're already in motion. Don't give me that stern look. You're already moving. Remember, objects in motion stay in motion. Duh. But there isn't the acceleration, the force of gravity at that actual point is a big fat 0. So you would simply maintain your speed. Now, what would happen as you sort of fell past halfway? You would decelerate. You would slow down. You would slow down. Okay? So, it says here, I'm going to read right back to the top. If you started at the North Pole end, you'd fall and gain speed all the way down to the center, then overshoot and lose speed all the way up to the South Pole. You'd gain speed moving toward the center and lose speed moving away from the center. Decelerate. Without air drag, the one-way trip would take nearly 45 minutes. Yeah, we're going to dig a hole all the way through. We'd have just enough time to fall. We wouldn't have time to dig. Forgot about the digging part. It would take you, if you jumped in a hole, From one side of the Earth to the other, it would take you about 45 minutes to fall all the way down.
And then you probably fall back the same way because of gravity.
Exactly. What would happen? Now, assuming that the Earth is perfectly spherical, if I were to jump in, feet first, 45 minutes later, clock, watch goes 45 minutes, what would happen to the Australians on the other side if there was a classroom exactly on the other side, a physics classroom in Sydney, Australia, and there was a hole that opened in their floor? 45 minutes later, what would happen?
We pop in there.
I would pop out upside down with my feet up in the air, exactly this tall, for a very brief second, and then I would fall right back in head first. It would be hilarious.
Would you eventually get stuck in the middle?
Good question.
Like
Now,
that.
that's all assuming no air drag, right? Now, obviously, there's air and there's lava and, you know, all that sort of stuff, right? If it was a vacuum, you would not get stuck. You would just simply, in fact, if I pop back up here in Canada 90 minutes later, if I didn't do this, if I step to the side, I'd be locked into this back and forth Australia-Canadian trip. Yes. If you failed to grab the edge, you'd fall back towards center, overshoot, and return to the North Pole in the same time. So it would take 90 minutes there and back. Who needs a plane?
That would get
Exactly. I was
boring.
gonna say that could be like a new way.
Yeah, that'd be awesome, right?
That'd get boring.
Repeat this trip with an accelerometer of some kind. Your acceleration, yeah, it's a thing that measures acceleration. Your acceleration at the beginning of the fall is g, but you'd find it progressively less as you continue toward the center of the Earth. Why? Because as you're being pulled downward toward the Earth's center, you're also being pulled upward by the part of the Earth that is above you. In fact, when you get to the center of the Earth, the pull down is balanced by the pull up. You are pulled in every direction equally, so the net force on you is 0. There is no acceleration as you whiz with maximum speed past the center of the Earth. Gravitational field of the Earth at its center is 0. How could you float in the middle? Like, how would you do that?
You have to stop.
How would you do that? You could touch the sides, yeah, like that, right? Probably, you know, maybe you don't have to wear gloves, right? If you were to actually, maybe if you had a ladder, if you climbed all the way down to the exact center and then jumped off the ladder,
You wouldn't do it.
then you could float. But you'd have to be
Make it really long.
right at the center. Right? And you'd want that ladder to go down a little ways past, because if you missed the center, right, you want to make sure that you had something to grab onto. Because if you didn't, what would happen if you jumped off the ladder a quarter of the way down? Would you come out in Australia?
Well, then you float.
And you'd never get out of that hole. You would be stuck.
Then you could grab back on the ladder.
Well, you'd have to make sure there was a ladder. It's okay, Hannah. It's not actually going to happen. No physics teachers were harmed in this demonstration. All right. Now, a few sort of legal disclaimers here.
Oh my goodness.
Interestingly enough, you'd gain acceleration. You'd gain acceleration during the first few kilometers beneath the Earth's surface because the density of surface material is much less than the condensed center. The mass of the Earth above you exerts a small backward pull compared to the disproportionately greater pull of the denser core material. This means that you'd weigh slightly more for the first few kilometers beneath the Earth's surface because you're getting closer to the more dense core. Further in, your weight would decrease and would diminish to 0 at the Earth's center. Okay, so if I asked you that question that's in a black box at the bottom there, if you stepped into a hole through the center of the Earth and made no attempt to grab the edges at either end, what kind of motion would you experience? Would you fall all the way through at a constant speed and stop when you reach the other side? No. Would you fall all the way through, speeding up the entire time and stop when you reach the other side? No. Would you oscillate back and forth with a changing speed, and we call this simple harmonic motion?
Maybe.
Or would you oscillate back and forth with a constant speed? Simple kinematic motion. The second last one, C. You would oscillate back and forth with a changing speed.
Where is that?
You don't have, I know, it's actually a clicker question, but because I'm computer challenged today, you don't have that, right? So you should, well, there's only a couple questions. You'll be okay, you'll survive. You should write in beside the black box there, the answer to number 1 would be, you would oscillate back and forth with a changing speed. Do I need to spell oscillate for you?
Yes. Probably.
No. What's the second word?
Oscillate.
Oh, oscillate what? Back and forth?
You would oscillate back and forth with a changing speed. And we would call this simple harmonic motion. Simple harmonic motion. Oscillate back and forth with a changing speed. You would speed up, right? You would speed up until you, and this is all assuming no air resistance, until you reached a constant velocity, which would occur right at the center. And then you would slow down as you approached Melbourne, Australia, and said, "G'day," and then fell back down the hole again.
So what would happen if there was air resistance?
You would reach terminal velocity and you'd never get to the other side. Because you wouldn't speed up enough. You wouldn't be going fast enough at the center to have enough speed to lose to get all the way to the other side. Does that make sense? Yeah.
So you would get stuck.
Okay. Yes, you would. Question number 2. Halfway to the center of the earth, would you weigh more? Halfway to the center of the earth, would you weigh more or weigh less than you weigh at the surface? Would you weigh more, less, or the same? Halfway towards the center. Halfway towards the center.
The same.
And the correct answer is you would weigh less. You would weigh less, and I'm going to read from the answer. Because the part of the Earth's mass that pulls you down is counteracted by the mass above you. There would be about a quarter of the Earth above you that pulls you up. It would also pull you this way and this way, sideways, right? If the Earth were of uniform density, in other words, if it was the same density throughout, it's not, halfway to the center, your weight would be exactly half your surface weight. But since the Earth's core is so dense, about 7 times the density of surface rock, your weight would be somewhat more than half surface weight. Exactly how much depends on the Earth's density, varies with depth, and where you drilled your hole, and all those kind of things that you don't need to worry about. Okay, but you would in fact weigh less. Now, you might notice that on the next page are the answers to those two questions that I just asked you. So they're there. They're there for you, yes. You can highlight them if you choose. Okay, so let's talk about weight and weightlessness, and we're going to do some notes on this in the future. Weight and weightlessness. You know what I'm going to do? It's on the next. All right, weight and weightlessness. The force of gravity, like any force, causes accelerations. Objects under the influence of gravity accelerate toward each other. We are almost always in contact with the Earth. For this reason, we think of gravity primarily as something that presses us against the Earth rather than something that accelerates us. When we're walking around often, minding our own business, we don't really think about gravity accelerating us because we're not being accelerated, right? But if you go outside and jump off a picnic table, are you accelerated towards the center of the Earth? Sure you are. Just not very long because, jumping off a picnic table is not very high. The pressing against the Earth is the sensation that we interpret as weight. Stand on a bathroom scale at a support on a stationary floor, like the one that I have here, right? I was telling someone the other night about my Newton scale, and they really thought that I was a nerd to have a Newton scale in my bathroom. Okay? Because it would look really nerd-like if it was in my bathroom. Here, it's it's fine. Physics class. People call me nerds all the time. Yeah, slightly, excuse me. Exactly. Okay. So, when I stand on there and it registers 800 newtons, that is 800 newtons of gravitational force due to the Earth pulling me down. The gravitational force between you and the Earth pulls you against the supporting floor and scale. By Newton's third law, the floor and scale in turn push upward on you. Located in between you and the supporting floor are springs inside the bathroom scale. The springs are compressed by this pair of forces. The weight reading on the scale is linked to the amount of compression in the springs. Now, could I calibrate this scale so that it shows me in kilograms? Like, could I just white out all the markings and change it to kilograms?
Yeah.
Absolutely. How would I do that? Just take every mark and divide by
9.8.
9.8, right? It's just the marking, right? All it is just a measure of how much push there is, right?
You just have to figure out each increment.
You just have to figure out each increment, exactly. If you repeat this weighing procedure in a moving elevator, if we were to take this bathroom scale and we were to go down to the DRCS elevator, anybody been in the elevator in the school before? It's a lot of fun, eh? It's pretty much the slowest elevator in the world, isn't it, Riley? Yeah. If you repeat this weighing procedure in a moving elevator, you would find your weight reading would not vary during steady motion, right? If I'm riding in the elevator on a bathroom scale, my weight's still going to be 800 newtons, right? But what if I was accelerated? What if at the start, I get in the elevator, it's at rest, and then I have to actually be accelerated up, right? How do you feel in a fast-moving elevator at the start? You kind of bend your knees a bit, right? Like you feel a little heavier, a little sluggish. How come? You actually weigh more. What would it show on the bathroom scale? If I weigh 800 newtons standing here, it might show when I'm accelerated, it might show 810. I actually weigh more. Because more force is required to do what? To lift me. But very quickly the elevator gets the top speed, and then the bathroom scale is going to go back to 800. And then as I get to the top, what's going to happen at the top? How do you feel at the top of an elevator ride? Yeah, you kind of, get that little sick feeling in your stomach. I would actually weigh what? Less. I may weigh only 790 newtons at the top. Okay? Because less force is needed to push me up.
Can we go do that?
Our elevator is not going to register. You're not going to see it. Okay? I can show you something though. Give me a second, I'll show you something. Okay? So it says here, if the elevator accelerates upward, the bathroom scale and floor push harder against your feet, and the springs inside the scale are compressed even more. The scale shows an increase in your weight. If the elevator accelerates downward, you're coming down from the CN tower. The scale shows a decrease in your weight. The support force of the floor is now less. If the elevator cable breaks and the elevator falls freely, the scale reading would register 0. You would be in free fall. According to the scale, you are weightless. Would you really be weightless? No, you are in a state of what we call apparent weightlessness, and it has nothing to do with mom and dad. I'm a funny guy. I'm standing on a chair, holding this scale, and I have a 1 kilogram mass attached to it. What does the Newton scale read?
8.
Almost 10. It should weigh
9.8.
9.8, right? Pretty close, right? Now, if I were to drop it,
Don't drop it.
I won't. But if I were to drop it,
It went negative.
what did it do?
It went to 0.
Did it go to 0?
Kind of.
Go over here so you can see, Steve. Do I need to do it on this way?
Yeah.
For you guys? Okay. All right. Ready?
Pretty much.
Did it go to 0? It should go to 0 when it's in free fall. Then my arm eventually runs out, and I have to stop it. And then, in fact, I actually have to apply a force against gravity, and it should actually weigh more.
I didn't see it way more.
Watch it weigh more.
That's too low.
Then the cable, I couldn't.
You gotta stand higher.
Yeah, let's do that. Yeah. So, are you actually weightless?
No.
No. What is that called? It's a state of apparent weightlessness. Apparent weightlessness. Okay. Flip the page over. Flip the page over. Or closely. If you define weight as gravitational force acting on an object, then you still have weight whether or not you are freely falling. Astronauts in Earth orbit who float freely inside their capsules are still being pulled by gravity and therefore have weight. But if you in the falling elevator and the astronauts in the falling satellites don't feel the usual effects of weight, you feel weightless. That is, your insides are no longer supported by your legs and pelvic region. Your organs respond as though gravity were absent. You are in a state of, and there it is, apparent weightlessness. But to be truly weightless, you would have to be far out in space away from the Earth and other attracting stars and planets, where gravitational forces are negligible. What does negligible mean? Minimal, so small you can ignore them. In this truly weightless condition, you would drift in a straight line path rather than in the curved path of an orbit. In a more practical sense, we define the weight of an object as the force it exerts against a supporting floor or weighing scales. According to this definition, you are as heavy as you feel. The condition of weightlessness, then, is not the absence of gravity, but the absence of a support force. That queasy feeling you get where you're in a car that seems to leave the road momentarily when it goes over a hump, or worse, off a cliff, is not the absence of gravity. It is the absence of a support force. Astronauts in orbit are without a support force and are in a sustained state of weightlessness. That causes space sickness until they get used to it. And I do have a video here for you, too.